Okay, so let's finish off today's concavity and point of inflection with example 6. It says here, by investigating the concavity of the curve y equals x to the 4, explain why the curve does not have a point of inflection. A sketch of the curve may be useful. Well, we already know what x to the 4 looks like, so if we had to sketch it, we know it's a smiley face, right? But it's like a smiley face like y equals x squared, but with a flatter bottom. So remember back in the day in the year 11 methods when we drew, oh, that was not good. And we started introducing polynomials. It's kind of like it's a smiley face, but a flatter smiley face. And then that was the turning point at 0, 0. Yeah, so that was y equals x to the 4, which we know and love from year 11 methods. So we need to explain algebraically as well why it doesn't have a point of inflection, right? So a point of inflection by definition is when your second derivative y dash dash equals 0 and then the concavity changes on either side. So let's prove this algebraically first. So y equals x to the 4. Y dash is 4x cubed, so y dash dash is 12x squared. Just differentiating one by one. So then, by definition, point of inflection occurs when your second derivative equals 0 and concavity changes either side. Well, if y dash dash is equal to 0, so that's 12x squared equals 0, so x squared equals 0, so x is plus or minus square root of 0, which in other words is just 0, right? So we have one theoretical point. Well, we need to check the concavity as well. So check concavity, we need to draw up a little table. We're checking for y dash dash, not the gradient, be careful. So y dash dash, we're looking at the rate of change of the gradient. So we're looking at a little bit to the left and right of our point 0. So negative 0.1 and positive 0.1. So y dash dash of 0 is 0 because that's what we figured out. Y dash dash is equal to 12 times 0.1, which will be a positive value, right? So if I go to use my calculator, 12 times 0.1, oh my gosh, I feel so stupid. Why did I use a calculator? Oh my, that's obviously 1.2. I feel so stupid. But anyway, it's positive, right? And then y dash dash is 12 times negative 0.1. I won't need to use a calculator for this. It's obviously negative 1.2. Oh my gosh, I did something wrong. Backtrack time. I can't read the question because y dash dash is not 12 times x, it's 12x squared. So go back, Miss Chan. Let's do that again. I feel even more dumber now, but that's okay. We learn. So let's learn how to read our writing. So y dash dash was 12x squared. Okay, so it's 12 times 0.1 squared. Okay, so 12 times 0.1 squared gives me 0.12, which is positive, okay? And then on the left, 12 times negative 0.1 squared, which is the same because a negative squared is all positive, so that's 0.12, which is positive. Now, that's not good in terms of point of inflection because concavity has not changed. My sign for y dash dash has not changed. So, we would write that the second derivative, does not change signs on either side of x equals 0. Well, what does that mean? So I'm just going to go up here, it's out of space. So therefore, concavity does not change on either side of x equals 0. So therefore, x equals 0 is not a point of inflection. So just because the y dash dash equals 0 does not mean it's a point of inflection. You also need the concavity to change on either side. So in fact, y dash dash is always positive, right? If you think about it, 12x squared, x things squared is always bigger than or equal to 0, and 12 times that is always bigger than or equal to 0. So in fact, y dash dash is always bigger than or equal to 0 for all real values, right? So therefore, the curve is always concave up because our y dash dash is positive. And then that is verified true because of our sketch. If you look at y equals x to the 4, it's a smiley face. You're happy. It's always concave up regardless for all x values. So there's no way that there's a point of inflection for y equals